Hello class, this is Physics for Engineers and in this video we are going to learn about torque. So by the end of this module, you are expected to number 1, define and give examples of the terms torque, moment arm, axis, and line of action of a force. Number 2, draw, label, and calculate the moment arms for a variety of applied forces given the axis of rotation. Number 3, calculate the resultant torque about any axis given the magnitude and locations of forces on an extended object. So first of all, let us define what torque is. So when a force is exerted on a rigid object pivoted about an axis, the object tends to rotate about that axis. The tendency of a force to rotate an object about some axis is measured by a quantity called torque, or it is represented by the Greek letter tau. As you can see, the Greek letter tau here has an arrow above it, so that means that the quantity torque is a vector. So the applied force F acts at an angle phi to the horizontal as shown in this figure. We define the magnitude of the torque associated with the force F around the axis passing through O by the expression tau is equal to Rf sine phi or Ft. So let us see this, review this figure. We have a wrench here. So the wrench is connected to a knot, and we use a wrench to tighten or loosen a knot to a bolt, right? So suppose that I want to turn this wrench, so I apply a force here, this force F at an angle phi. So this wrench will rotate in this direction, going right. So let me so the direction is counterclockwise, right? So the force that is effective, the effective force that causes this rotation is the y component, right? So if we break down the force F into two components, the x and y components, as you can see, the force F cosine phi here has nothing to do with the rotation because it is in line with the axis, okay? But the y component is perpendicular to the axis of rotation, so it causes the rotation. So that's why our formula for torque is Rf sine phi or Ft, okay? So let us define some terms. R is the distance between the rotation axis and the point of application of F. So in this figure, this is our rotation axis. This is the point where everything rotates. Everything revolves around. So the distance from this point to that point is the R, or radius if you want to call it radius. Meanwhile, D is not similar to R, okay? So D is the perpendicular distance from the rotation axis to the line of action F. And the line of action of a force is an imaginary line extending out both ends of the vector representing the force. So suppose that this is the force and we want we want to draw the line of action of this force. So the line of action, and if you draw the line of action and you draw a line starting from the rotation axis to the line of action, so the point where the line of action and this line from the pivot point is perpendicular, so the length of that line is your D. So F sine phi and R should be F sine phi R and F D should be equal in magnitude. So the quantity D is called the moment arm. So this is the moment arm or level arm of F, and the rotating tendency increases as F increases and D increases. So you can actually observe this in everyday objects. So if you use a longer wrench and with the same if you use a longer wrench and bigger force, the rotating tendency increases. So that means the torque increases. Meanwhile, sorry, if you use a shorter wrench, then the torque decreases also. So what about if two or more forces act on a rigid object to cause torque or to cause rotation? So as shown in the figure, I have two forces here acting on a similar object and on the same object. So if these forces act on a rigid object as shown, each tends to produce rotation about an axis through O. So the axis, so as you can see, they're not they're not parallel or something. They may be intersecting, but they have different points of application. So where would the object tend to rotate? So the object will rotate at a point where the line perpendicular to the first force F1 and the other force F2 intersects. So this is your point O. This is where your body tends to rotate about. So that is the summation of the torques here is equal to tau 1 plus tau 2, which is equal to Fd1. So this is your moment arm D1 minus Fd2. So F times moment arm D2. So why is there a negative sign here? So let me be clear about the sign conventions here, okay? So conventionally, we consider counterclockwise rotation, so like this, counterclockwise against the clock, as positive. So suppose that you have a string here. Suppose that you have a string here and it is connected to your force, vector force. So if you rotate that vector force about this point and you have a string here, this vector force will rotate in this direction. So that direction is counterclockwise. So that is positive. How about the other? So suppose that I have a nail here and it is connected to a string which is connected to the other vector. So if I rotate this vector about this force, so what is this direction? This is clockwise, so we have negative, right? So another method here on how to get the correct rotation is use the right hand rule. Put your right hand here. So let me draw that. Suppose that you put your right hand here, then put your thumb up, then curl your fingers in the direction of the force. So the direction of the forces here is this way. So you curl your fingers here, and your thumb points upward, right? So that means the sign is positive. How about the other one? So put your right hand here and curl your fingers in the direction of the arrow of this vector. So in doing that, you need to put down your finger, right? You need to make a thumbs down gesture. So that means the direction of your thumb is to downward. So that means that the sign is negative. So whichever method suits you, just to get the direction of the sign of the torques right. Okay. So torque should not be confused with force, and also not to be confused with work. Forces can cause a change in translational motion as described by Newton's second law, and can also cause a rotational motion, but the effectiveness of these forces in causing this change depends on both the magnitudes of the forces and the moment arms of the forces in the combination of we call torque. Okay, so I hope that's clear. So let's proceed. So where is torque useful? Torque is useful um, in determining the equilibrium of a system. So if we can remember our past lesson, I think it's lesson kinematics about equilibrium. Okay, so equilibrium is the state of having balance. So the two conditions for equilibrium for a rigid object under the action of coplanar forces. So coplanar forces means force that acts on the same plane. So these conditions are: number one, the first or force condition, the vector sum of all forces acting on the body must be 0. So you have already studied this. And the second condition, or the torque condition, is that the sum of all the torques acting on the object must be 0. So using the positive, this notation means that taking the positive sign as the counterclockwise direction, the summation of torques is equal to 0. So those are our two conditions for equilibrium. So let us have an example to demonstrate our understanding of the subject. So find the torque about the axis A in the figure due to each of the forces shown. Okay. So the solution for this is the easier way to do this. That is RF sine phi. But if you want the harder way to do it, then you can use the formula tau is equal to Fd, in which d is the moment arm. So in this figure, it is illustrated. The moment arm here is illustrated. This is the moment arm. Okay, so going back, for the first force, 10 Newton, tau is equal to Rf sine phi 0.80 times 10 Newton times 90. That is, the answer is negative 8 Newton meter. So why did we not change the sign, put the sign here? Why did we not put negative here? But we still managed to get a negative answer. So the answer is take the positive x-axis as your reference point or reference line for measuring the angle. So from this point, from this axis to your vector, we have negative 90. So this is supposed to be negative 90. So we will arrive at negative 8.0 Newton meter. But sorry, I think I just forgot to put the negative sign here to denote that this force will cause a clockwise rotation about the pivot point A. So that should be negative. The torque is negative. So about for 25 newtons. So for 25 newton, so as you can see, this force will cause a counterclockwise rotation about the pivot point A. So I put a string here, then I try to rotate that, or I use the right hand rule. Then my direction is positive, my sign is positive. So 0.8 times 25n sine 25, that will give me 8.5 Newton meter, and that is positive. So you can also do it the other way. So to find the moment arm D here, so use the Pythagorean theorem or the sine cosine laws, and take note that this is a right triangle. So to get the moment arm, I just need to do sine. So the sine law, sine is equal to opposite over hypotenuse. So that will give me the same answer. How about for 20 Newton? So 20 Newton, the force 20 Newton is collinear with the pivot point A. So the line of action of that force passes through point A. So that means, or the torque is 0. So you can also prove, if you don't believe that, you can just plug it in the equation. So tau is equal to 0.825 sine 0. That will give you 0 Newton meter. Okay? So how about for cases where we need to find the net torque? So in this example, a one-piece cylinder is shaped as shown, with the core section protruding from the larger drum. So this is our one-piece cylinder. The cylinder is free to rotate about the central z-axis, shown in the drawing. A rope is wrapped around the drum, which has a radius r1, and it exerts a force T1 to the right of the cylinder. A rope is wound around the core, which has a radius r2, and it exerts a force downward on the cylinder. What is the net torque acting on the cylinder about the rotation axis? And suppose that T is equal to 5, R is equal to 1, T2 is equal to 15, R is 0.5. What is the net torque about the rotation axis, and which way does the cylinder rotate starting from rest? Okay. So let us break down this problem first. I think you're already familiar with the z-axis. This is the 3D coordinate system. So in this, you don't need to fear this z-axis, because we're just looking at it as the rotation axis. This is the point where this is the axis where everything rotates about. So in our previous problem, we have that axis as a point. So if you are still confused about this, just think of it as just a point. It's just a point, right? If you look at it from the top view, it disappears and just becomes the origin. So, but what is important, that it is the axis of rotation. This is the axis where everything rotates about or revolves around. Okay? So to solve this equation, this is particularly easy, because what you need to understand is just tau is equal to force times radius, f sine phi times radius. Then just figure out the correct sign, whether it's positive or negative. So proceeding, we have two forces here, right? T1 and T2. So which direction does T1 about, if this is the axis of where T1 rotates, the cylinder rotates, if this is the axis Z, so what direction, and this is our force, so what direction would the force T1, what direction would the force T1 give the cylinder? So using the right hand rule, we can figure out that this one causes the body to rotate clockwise. Okay, so that gives us negative T1 R1 plus, how about the other force? So this one, using the right hand rule again, you can see that this force causes the body to rotate on a counterclockwise manner. So like this. So we have negative T1 R1 plus T2 R2. So that is our net torque, the equation for our net torque. So how about for letter B? So for letter B, we just plug in these values. We have T1 R1 plus T2 R2. So negative 5N times 0.5 meter, times 1 meter plus 15 and times 0.5 meter. We get 2.5 Newton meter. So which direction does it rotate? We can see that the summation of torque is a positive number. So that means that if you can recall, all the positives are counterclockwise and all the negatives are clockwise. So since our result is positive, that means the rotation is counterclockwise. So that's it for today. Um, I hope you learned a lot, and the next lesson we are going to talk more about the dynamics of rotation. See you then.